Let us suppose that we didn't know anything about the reactivity series, but we are given 4 metallic elements: magnesium, iron, copper, and silver. And we are asked to design an experiment to create a mini activity series. But we are also told that we can have aqueous solutions of their salts. Okay? So we have magnesium here, and you have magnesium sulfate, you have iron here, you have iron trichloride, you have copper here, copper 2 sulfate, and silver nitrate. How will you design an experiment to create this mini reactivity series? You can pause the video or you can think about that. Not you. Okay, but we still have to go on. This has been described on page 96 of the text. What we'll do is this. We'll take each of these elements here, okay, and we'll dip it into each of these separately and absorb. If a precipitate is formed on this metal here, it will tell us that this metal is more reactive than the one from which the salt is made. Okay, so we'll start the experiment by, first of all, introducing this magnesium strip into each of these and observe. Wherever a precipitate is formed, we have the table here. I'll put a check mark to indicate that this element here is more reactive than that one. So we first of all put this magnesium strip into magnesium and observe nothing happened. So we wipe that off clean, okay? Then we take this magnesium strip and insert it into the iron now. You see? We did get a precipitate of iron on this strip here, okay? You put a check mark against iron. Now we'll have to clean this out. Or maybe we can break that off, insert it into the copper. Immediately, you see we get a deposit of copper on the strip. We make a check mark here against copper. And finally, we'll put it into the silver nitrate solution. And immediately you see we get a deposit there. So it means that magnesium is able to react with iron, copper, and silver there, okay? So put a check mark against silver. Now we'll use iron. Insert it into the magnesium. Wait for a few seconds there. Nothing happened. No check mark. You put it in iron itself. Of course, iron will not be able to displace its own self. Doesn't matter how long you put it there, you're not going to get anything. We clean it off. We now put iron into the copper and observe. Immediately we see a deposit of copper onto the nail here. You can clean it off or you can use a different nail to put it into the silver now. Immediately you can see a deposit of silver on the iron nail. So we put a check mark against copper for iron and silver. Now we'll take the copper rod, put it into the magnesium for a few seconds. You see what happened? Nothing. Into the iron. No change. In the copper itself, you don't expect anything to happen. Copper will not be able to displace its own self. Nothing there. And then we take it and put it finally into the silver. And you can see immediately, look, you get a deposit of silver onto the copper. All right? Finally, so we take a check mark against silver for copper. Then you put silver there into magnesium sulfate, nothing. Into the iron, no change. Into copper sulfate, no change. Into itself, no change. So no check mark there. Predicting the spontaneity of redox reactions. It is a reducing agent that donates the electrons to the oxidizing agent. In the example studied so far, it is the metal atoms that are acting as the reducing agents, and the metal ions that are acting as the oxidizing agents. To predict whether or not a redox reaction will happen, it is important to know how strong or weak the reducing and oxidizing agents are that are mixed. Most likely, a redox reaction will happen if a reaction takes place between a strong reducing agent, the electron donor, and a strong oxidizing agent, the electron acceptor. We will use the results of the preceding demonstrations to create a mini table of the relative strengths of the oxidizing and reducing agents that were used. According to this table provided, we can see that magnesium was able to displace all other metal ions from solution except its own. That was followed by iron that was able to displace silver and copper, but not able to displace magnesium and itself. Copper was only able to displace silver, and of course silver was not able to displace any of these. Based on these results, the relative activity of the elements can be ranked as follows. Magnesium being more reactive than iron being more reactive than copper, and copper being more reactive than silver. The element that is most reactive is the one that has the greatest ability to donate electrons. It is thus the strongest reducing agent. Ranked in terms of their reducing strengths, we get magnesium being the greatest reducing agent, followed by iron, followed by copper, and then silver. The strongest oxidizing agent in the table above is the one that is capable of doing the most oxidizing. Based on the results, the iron can be ranked as follows in terms of greatest oxidizing strengths. So if you have a quick look at the table, we can see that the silver ions are able to oxidize all of these. And that was followed by copper ions that are able to oxidize these, followed by iron. And the one that was not capable of oxidizing anything was the magnesium ion. So based on that, we have this ranking here for oxidizing strengths. Silver ions being the greatest oxidizer, followed by copper ions, iron ions, and magnesium ions. Making lists of these in terms of their oxidizing and reducing strengths, we have for the oxidizing agents, silver at the top there, followed by copper, iron, and magnesium. In terms of the strongest reducing agents, we have magnesium at the top of the list there, followed by iron, followed by copper, followed by silver. Notice how the ion formed from the atom of the strongest reducing agent now becomes the weakest oxidizing agent. This is the strongest reducing agent, and this is the ion formed from it. See how it now becomes the weakest oxidizing agent. And the atom formed from the ion, that is the strongest oxidizing agent, becomes the weakest reducing agent. The strongest oxidizing agent was silver ion, and the atom produced from it becomes the weakest reducing agent here. Scientists have performed several types of experiments that have allowed them to determine the comparative reducing strengths of a list of other metals and their comparative oxidation strengths of their respective cations. And these can be retrieved from a book of data. How can we use the results obtained in our mini activity series to determine the spontaneity of redox reactions? Let's suppose we wanted to predict whether or not the reaction between copper and magnesium sulfate is spontaneous. So the reaction can be represented by this chemical equation here. Breaking it into its ionic equation, we get copper atoms reacting with magnesium ions, sulfate ions, to produce copper-2 ions, sulfate ions, and magnesium atoms. Removing the spectator ions, which are sulfate ions in this case, we ended up with the net ionic equation, which is copper reacting with magnesium ions to produce copper-2 ions and magnesium atoms. The next thing we'll do is to show how electrons are gained and lost by the species involved for the reaction to have happened. So, according to the net ionic equation, copper atoms are changed into copper-2 ions, and magnesium ions are changed into magnesium atoms. For that to have happened, copper must have lost 2 electrons to produce copper-2 ions. And of course, that process represents oxidation. And for a magnesium ion to form a magnesium atom, the magnesium ion must have gained the 2 electrons produced by the oxidation of copper. In this case, a reduction would have happened. Comparing the reducing strengths of the 2 metals, copper and magnesium, in a net ionic equation, we see that magnesium has a greater reducing strength than copper. We can go back to our list to verify that. So we're seeing that magnesium, according to this list here, is a greater reducing agent than copper. Comparing the oxidizing strengths of the 2 cations, magnesium 2 plus and copper 2 plus ions, in a net ionic equation, we see that copper 2 ion has a greater oxidation strength than magnesium 2 plus ion. Verify that in the table. Copper is up here, magnesium is down here. Copper 2 ions have greater oxidizing strengths than magnesium 2 plus ions. In this case, the stronger reducing agent magnesium should be losing electrons, but it is not. Instead, copper is losing electrons. Also, the stronger oxidizing agent, the Cu2 plus ion, should be gaining electron, but it is not. Instead, it is a magnesium 2 plus ion that is gaining electrons. The reaction will thus not proceed spontaneously. Another example of a single displacement reaction that we are trying to ascertain if it will take place spontaneously or not is the reaction between iron and silver nitrate to produce a solution of iron 3 nitrate and silver. Right in the ionic equation for that reaction, we get an atom of iron, 3 ions of silver, nitrate ions, Fe3 plus ions, silver atoms, and nitrate ions. We see that nitrate ions are common on both sides. We call these spectator ions. And to obtain the net ionic equation, we remove them from the equation. We're now left with what is called the net ionic equation, that's represented as an iron atom reacting with 3 silver ions to give you an ion of Fe3 plus and 3 silver atoms. Now we have to show how the electrons are gained or lost by the various species involved for the reaction to have happened. For an iron atom to be changed to an ion, this iron atom must have lost 3 electrons, and that would have represented an oxidation reaction. For the 3 silver ions to become 3 silver atoms, these must have gained the 3 electrons produced by the oxidation of iron, and this reaction would have been reduction. Comparing the reducing strengths of the 2 metals, iron and silver, in the net ionic equation, we see that iron has a greater reducing strength than silver. Let's verify that from the table. So here is silver, this is iron, and that is silver. Iron is a greater reducing agent than silver. In this case, the stronger reducing agent, Fe, is losing electron, and the stronger oxidizing agent, Ag+, is gaining electron. The reaction will thus take place spontaneously. So as a general rule, we have the following statement. The general rule is that for a reaction to proceed spontaneously, the greater reducing agent must be losing electrons, and the stronger oxidizing agent must be receiving electrons. And that is what took place here. The stronger reducing agent, when you compare iron with this one here, is losing electron, and the stronger oxidizing agent, when you compare silver ions with iron ions, are gaining electron. As a result of that, this reaction is spontaneous, as opposed to what happened before, where the weaker reducing agent is losing electrons and the weaker oxidizing agent is gaining electron, As a result of this, the reaction was not spontaneous. Thank you for listening.